My name is Chandra. The topic for my discussion is actually rapid pruning of search space through hierarchical matching. There are a lot of words in there, but bottom line is you're trying to cut search and obtain the best performance you can with Lucene and Solr. My background briefly, I'm a machine learning scientist at ThreatMetrix. The company is in the business of preventing cybercrime. And the task I'm actually going to present is related to that company. I'm also a co-chair of developer programs at IntelliFest. IntelliFest is a forum that actually brings in a lot of people in the area of AI, machine learning, and big data. And we have a conference coming up in October. You can look up that information. Career path, I've spent a lot of time in R&D at Siemens Corporate Research in the field of learning and expert systems. I've worked at Donaldson, Lufkin, and Jenrette, which is a Wall Street firm those days. I worked in the artificial intelligence group, building a product for network monitoring, and worked on several startups which are related to classification, crawling, security, and financial trading. So the outline, the presentation is kind of balanced. It has something in for people who are in the background in research, project management, development, as well as testing. Okay. I briefly go over the task that we're dealing with and talk about all possible approaches that you can take, and then talk about why we settled on the search paradigm for solving the problem. And hierarchical matching is just a matter of squeezing out more performance out of the system. Okay. Then present the results based on what we have, and finally acknowledge the team that has actually worked with me on this. The device identification task is basically ThreatMetrix receives a lot of device information from customers. Okay. And this is an entry point into a workflow system that predicts whether somebody is a fraud or not. Okay. And the kind of attributes we get a whole bunch of attributes. And the task is to basically classify in a very short time what you think that object is, the device. And it could be one of, you can call it either a label, signature, class, or a hash. But classifying the device has to be done in real time, and it has to be very accurate. Key thing is, of course, when devices come back, you classify them correctly, and you're able to retrieve the object back within a certain range of tolerance. And if you have never seen this object before, then what you do is you create a new class and start tracking it. Okay. Ultimately, there is a data retention policy where you probably want to keep data just for about 2 or 3 weeks. And then some of these devices age out. The challenges we have in this one is, some of the challenges, the attributes are extremely volatile. Okay? One single change in any attribute can have a propagation across. So it is very difficult to predict what the next state is going to be. All right? There are no pivot attributes, meaning by it is not possible to take the entire class and say we'll divide this or group this into a particular category and then solve this in a hierarchical fashion. That doesn't work. For example, if you say we're going to put all devices that are coming from Windows machines into one category and then start refining the search, you soon find out that the attributes that actually you got the result from do not really match something else. Okay? So you have to do a collective judgment or a multidimensional search in order to arrive at the particular class. Also, the distributions change over time. So if you have seen a certain profile of an object, within 2 weeks it can change completely because they have plugins and they have all other parameters going into the system. And the signature might change considerably. Okay? All in all, the key thing is that it's very different from a regular search problem, where if you don't locate a Pizza Hut within a mile or something, it's not a big deal. But here, if you actually misclassify, it is a problem. There's an impact on the revenue. And also, if you classify a good customer as fraud, that has more repercussions. Right? And the response time is very critical. We have to get back within 100 milliseconds. It is not a typical search problem where you say sub-second, and that's about it. More on the challenges we have. If you're given sufficient time, right, you can do a lot of search, you can do a lot of analysis on the data, and ultimately come back and say, OK, this is what I think it is. But we don't have that luxury. And from the project management point of view, we started classifying devices which are about 28 million in our repository. And by the time we are not even done completely with the project, we're already dealing 10 times more. Right? And if you look at the load, that has not changed very much, a factor of 1.5. But the latency doesn't change. In fact, it goes the other direction. So you have to continuously scale in order for you to be able to keep up with the changing distribution. It is not because the project management is changing the requirements. It's because the customer base is expanding. So some of the approaches you can take, we can probably capture a whole lot of devices using rules, right? Or you can use learning models. You can induct some sort of a learning model based on the data. And the last option that we are looking at is the vector space model. Basically, it's a retrieval engine. But whatever we do, we have to provide an enterprise-grade solution, right? I mean, it is not enough just to solve the problem, but also be able to take care of all the other things like fault tolerance, redundancy, and so on and so forth. Am I speaking at the right rate? Not too fast, OK. The first thing is that if you're trying to solve something using rules engine, you don't really have too many experts out there. And even if they give you a lot of rules, I mean, you're not able to keep it up to date. So there's a real large maintenance issue if you're trying to go into that direction, right? So it is not a viable approach, right? Learning models. I mean, a lot of people throw data at learning models, and they assume that the model is going to discover something. OK, now let's look at this problem, right? Most of the machine learning methods you look out there, they are dealing with binary classification or a limited set of target classes, right? To learn, I mean, we have a huge number of classes, right? Almost 70% of the devices you see belong to a class of some sort. So we have very few examples to go by or train any particular learning model, right? The attribute values don't have any bounds. I mean, literally, for example, user string or a browser string, it can have any number of unique values. So you don't really have a bound on that. And they don't follow a natural progression. If you see somebody's device is coming with a certain screen resolution, it's not going to be predictable what the next state will be like. Okay? So there is no natural progression for that. So when you don't have enough training data, right, and you don't have any clue of what to do, then you throw it into a clustering kind of model. They are great. They will definitely do something. But the problem is a lot of things start looking the same, right? And so the practical value doesn't exist. Ultimately, if you build a model, and if you misclassify something, the customer is going to ask you what exactly happened. And if you use something like a neural net or any of the other methods, you cannot actually explain what happened. You can just say, oh, the data told me so. I mean, but that's not good enough for us. And they tend to ignore any domain knowledge that you have, right? I mean, ideally, you always have some knowledge about the system, and you want to say something, but there is no way to feed that into a learning model. I mean, you've got to implicitly introduce some bias. So it is still a challenge to provide the enterprise solution. So the first thing is that we don't have a comparable application out there that actually has these requirements, okay? But we do want to deploy a classifier that not just explains itself, but it scales over time and is able to respond back in a very short time. And we have some domain knowledge, and we want to use them, right? And the only place where we'd like to use machine learning is actually to improve the classifier, because you do have feedback on the system when it goes into the field, and you can analyze how well it did, and then use some reinforcement learning or otherwise to improve the system. If you look at the problem, right, it fits naturally into kind of a retrieval model where some attributes can change, but you can still focus on what you think that object is. So vector space models are really good at that. And the only trouble is that a little change in one of the, let's say, rare attributes can kind of bias the output. So you may not be able to get the accurate result right on top. So there is some kind of work that has to be done at the top of this retrieval engine. So when I started this project, it was basically in Lucene, and then looked over all the documentation that we had in Lucid Imagination, a whole bunch of it. And there were lots of case histories that I looked at, and started the project using Lucene and Solr. And then a team came on board, and they were all from C++ world. They took just about a week to install Lucene and learn the entire thing. So the learning curve was very, very short, okay? And that was very helpful. We didn't throw the entire data of a device at the Lucene Solr engine. Instead, we started working on the attributes. So the way I did that was actually using the core admin UI. When you index some of the documents, you actually get a lot of histograms. You get the frequency information. And you can tell, I mean, some domain knowledge, you can tell what is primitive and what is actually derived data. And you can also look over things like entropy, how much information particular attribute carries. And you like things that are having sort of a spread. That means every attribute has some say in the classification of a document. And these are kind of, they're not ad hoc, but slightly disciplined way of selecting the attributes rather than giving the entire set for indexing. One deviation from the natural, let's say this entire application is kind of unorthodox. Not all of it is text, okay? If you look at a device plugin, for example, there isn't much text out there. There isn't any grammar or semantics or anything. A browser string has no meaning at all, literally. It has a long sequence of strings, and it comes with information that you cannot really run any text engine on that. So the first approach, in any case, we used Lucene and Solr and treated the entire thing like a sentence, right? Used a bag of words. The only problem was that it was very, very quick, but the relevance was not there, right? The top hits don't give you what you want. And if you end up using all the fields instead of a bag of words approach, then it becomes very slow. You do get the response finally, but the response is accurate, but it takes a lot of time. So there is this feature called disjunction max. So that's exactly what we wanted. We wanted something where some of the attributes can change, but we are still able to hone in on what we think that object is, okay? And disjunction max as a property for us. So we decided this is exactly the feature we want. We're going to go ahead. And the description, actually, I took it from Search Hub. There's a blog written by Hossman, and you can actually look at the information for that. But the ideal thing is that not a single term. IDF has this flaw. It's not a flaw, but the property that one single attribute can completely hijack the classification, because it appears as a rare plugin, it makes a change, and suddenly it looks as the most important thing. But disjunction max ensures that everything is collectively looked at, so a certain number of attributes are to match. We were in scenario 1, where we basically experimented with multiple fields and used about 3 phrases to describe the entire device, and a minimum match of 2 clauses. That's all we asked for. That means we allowed about 35% change, 33 to 35% change. And all of them generated must-match clauses. And the latency was about 35 milliseconds, but precision was 80%. And the remaining 20%, we couldn't really match many of the documents. The problem was that within a clause, if there is a change in the middle, will fail. The disjunction max will fail. And the typical scenario is that if you look at the user base, 80 to 90% of the people are actually good people, benign. The transactions are benign. The fraudsters are in the range of about 5 to 10%. And if you don't catch that 20%, you're going to miss out. And that is actually crucial for us. So we actually failed in that scenario. We put our system out there, and it didn't pass QA. And we went back to the drawing board. And in scenario 2, we said, OK, we're going to treat all the fields as terms and everything, and have just one Solr field, but we'll ask for about 50% match minimum. This is great. So most of them end up being a should match clause. It is not a necessary match. The latency was dismal. It became 2 seconds, but the precision was very good. So you're kind of having a middle ground here. On one case, you lose out on the precision. The other case, you're losing out on the latency. So possible workarounds, either you can do a deep dive into Lucene and then try and install some sort of a branch and bound search that actually takes your domain scoring and is able to reduce the amount of search you want. Or we could try and minimize the number of candidates that go into dismax. Given the time we had for the entire project, this was the option we took, right? And at that point, we didn't know whether we'll actually achieve what we wanted. The first thing is that we want to reduce the total number of Solr units that we're going to search, the instances, and try and come up with a way that you can reduce the terms. In our experiment, when we added a term, we doubled the time in dismax. And that was before we did any dedupe, okay? But it was a scary thing, because it is a good thing in one sense, because you can drop a few terms. And if you can maintain the accuracy, then you can lower the latency, right? So if you look at scenario 1 and 2, the lesson you learn is that you want to use as many phrases as you can, at the same time minimize the number of terms, right? So what we did was we actually used Cooccurrence matrix. In fact, we've heard this about 3 times today. So we extracted the most common phrases and used some sort of analysis on statistical analysis offline. And we were able to predict that these are the terms that always occur together, adjacent or at a certain distance of 1 or 2. And if we chose a phrase, then the equivalent terms that actually built that phrase were deleted, right? So we don't use them in the search. Every single stop word that we added dropped the time significantly, okay? And in order for you to determine the stop words, you have to go back, because your lexicon has changed from just terms to phrases now, and you have to still establish what the stop word should be. And in doing all this, we keep track of the regression test. We always make sure that accuracy is maintained. We never want to lose the accuracy part of it. This entire process actually reduced the dismax terms by about 30%. Okay? Okay, as a digression, I just want to say there are certain things that I bring from a background. I'm predominantly, and I've worked in the area of AI. So some of the papers there deal with how do you cut search. But the search they're talking about is slightly different. Here, when we talk about search and information retrieval, we're talking about number of hits, right? How do you reduce that? There, they're talking about a search space of possible things that you can explore. But all these are relevant papers that actually help us to apply some of the technologies here. So roughly, the concept looks like this, right? At this level, we receive the transaction, which is all either in a CSV or JSON format. And it turns out to be just a bag of words. But we pull up phrases based on the analysis we did. And we also look at the entire thing from a distance and say, what kind of score can I come up with as a whole? I mean, we take the entire transaction, and we compute about 5 or 6 statistical parameters, okay? Then what happens is the phrases actually feed into dismax. Okay, this part reduces search already. But the models feed into the Solr instances that you want to search. That means even if you have number of servers, distributed search doesn't go to all the units, okay? And there is in between, you see the domain-specific patterns. These are things that we know about. For example, certain plugins only occur with certain operating systems. So that kind of domain knowledge is actually plugged into that information box there. And it is used both for filters and for verification later. So what you have done is, to some extent, you've reduced the matching, the entire thing being done in Solr, right? Instead, you have reduced it to just selection part. The selection is done by Solr, but the verification and otherwise is done by your domain knowledge. Okay, it's not a flaw, but we know that the Solr score is not normalized across shards. So when we get the top 3 or 4 candidates from every unit, we ultimately have to put them together and still rank them, right? And the ranking is based on the custom verification module that we have. So we are not dependent on what Solr provides. We are actually pretty much buffered and insulated from that kind of a scoring flaw. And if the deduping is done, we literally always match on the correct documents that we want. And ties are broken. Ultimately, if you have 2 documents coming out of 3 different units, 2 documents coming out of different units, you can still look at the time difference and then resolve the tie. If you have found a match, the best match with a certain, beyond a certain threshold, then that is declared as the best match, and it is persisted in the database, and then you return the custom score. Some of the comments, just to review. First thing is that dismax performs exactly what we want in terms of a multidimensional search. The extracted filters help us to hierarchically arrange everything so that we don't deal with all the details at one time. And we are able to come at certain stages and just handle the entire thing. And the key thing is that we separate this evaluation and the selection, okay? This is where I think there is a slight difference between how we use Solr and what is normally Solr used for. So most of the time we spent in the entire project was in attribute selection, okay? If you have 200, 300 parameters in the device, we end up selecting only a subset of them. And ranking, ranking we spent a lot of time because it's domain related. Because you've got to be so precise, you can't afford to have the so-called best match sitting on the 3rd or 4th in the list. It has to be right on top. Optimization, you always have to spend a lot of time because it is still Java technologies, and in order for you to squeeze out the performance that we want, we spent quite a bit of time in optimization. Index regeneration. Every time we had a test case where we changed the attribute, we had to reindex. We had to reindex. And regression testing is always done because of all the changes that we made during the development stage. At the last stage, what we did was we finally took the best practices out of scaling Solr and applied some of the techniques related to basically quite a few things. Like omitting norms and omitting positions, because those things don't matter when you have a phrase level search. They matter when they're all terms. When they're raw words, they matter a lot. But once you go into the phrase stage, they all look like a hash, and you don't really care about the positions and stuff. I think there's also a case study from Lucid Imagination that we used. How did we do testing, right? One thing is that the best match you can possibly obtain for any document is its self-match, right? So we would index a whole bunch of documents and take the same set of documents and convert them into queries and try and see whether we are able to actually spot them, right? And if, in this case, we were actually able to produce about 99% accuracy. We did further optimization, we can get even close to 99.9. In terms of latency, we had a custom harness that actually used a server and an agent. At the same time, one of our team members integrated the entire thing with JMeter, so you can get a real feel for the kind of throughput that we need. We used Solr meter at one point, but Solr meter has the dependency on an admin UI, and if you want to deploy it as a command line tool, that doesn't work. So what you're looking at is this is where we were, right? And then we did a whole bunch of optimization. So we want to be at 100 millisecond median response time, right? That's what we want. But here, we are somewhere like 500. And then we implemented the hierarchical match and focused the search using models. We were able to reduce the search to, let's say, about 350 or 400 here, right? And we did further optimization using domain patterns and then adding stop words that come out of phrasal analysis, right? And deduping, using native deduping in Solr. Now we are actually at a point where we are about 100 millisecond response time. We want to squeeze out a bit more. The last portion here, the tail, is actually the dismax part. Most of the things actually end up there, and dismax slows it down. Throughput is about roughly, I think, 50 transactions per second. And the response time, if you look, we are close to about 100. And that was a target for the initial system. The way we execute, everybody follows the agile methodology in the team. And at any point, we always had 2 or 3 plans, okay? We always consulted as a team, and we would come up with what should be the first thing to go after. And then we always had contingency plans, right, at every stage. But in most cases, the primary plan worked out the best. Half the team in development worked on rapid prototyping. So the course was, if you look at the code, it is not all that cleaned up or anything. But we try and get the basic idea to work. And then we'll hand over to some of the people who are really good at software engineering, so they would make it production quality. The key thing here is that all this time, I've been talking about how do you get the primary server to run. And in order for us to do things like redundancy, replication, all that, we are evaluating data stacks at this point, and also keeping Solr Cloud as a possible second plan. So what are the things that we learned from this entire project? First thing is that Lucene and Solr, majority of the time we're talking about text. But in our case, it doesn't look like text at all. Once we look at the tokens and phrases, it's all hashed. The thing is, it's not whether you can solve a particular classification problem, whether you can prioritize among the many ways of doing it. Okay? There are multiple ways of doing the same solving the same problem. The nice thing is that we never got stuck in the entire project. We were using open source tools, everything, but there's never a stage where we were like, hitting a roadblock. At all times, we found that somebody else had this thing discussed on the blog or something, and we were able to address that. The key lesson, the first mistake we made in the beginning was to look only at the response time. Big mistake. We should have really gone after accuracy. If you don't get the accuracy, there's no point trying to do anything more. But if you have all these 3, like precision, latency, and scale as requirements in your project, you will end up doing something like abstractions. There is no other way you're going to get performance. And you can't possibly index once and run anytime, anywhere, because during development, you're going to be doing it all the time. Unless you have a lot of hardware where you have Hadoop jobs and others, you will end up repeating this cycle quite a few times. So this one goes back to the abstraction thing. You cannot throw everything at Lucene and Solr and not analyze the data. That kind of classification is not going to work. Rapid prototyping is a great idea to do, but you will fail a few times. So this is the basic message that we want to give, is that you don't try and match at the lowest level in Solr. Instead, you try and match at a higher level, raise the level of abstraction if you can, but you have to analyze your data on your own, right? And before I get to the last, Let me give my contact information here, if you can send your comments and feedback. And then I want to recognize the team. Fong actually worked on a lot of the research quality. And then we have Luke Mertens, who is actually in the audience. He worries about the productization, scalability. He set up the JMeter framework. We have Brent Pearson, who did a lot of integration work, he's right here, and also does release management. Tracy Shu is a person who actually tripped us many times. She was in QA, but she would break the development thing, and she was a real barrier to cross. So, but she did a great job. And we ended up doing a lot of revisions based on that. And then we have Srinivas right there, who goes freely between development and QA and really communicates all the needs and everything and takes care of deployment. So collectively, we want to thank LucidWorks for the opportunity to present the thing, and thanks for your time. Questions?